So with this problem, we've got an infinite wire with a charge density of lambda, and we're considering a point up here, which is a distance a above the wire. And we're asked to start by considering a little increment of the wire here with a length dx, which is a distance x from this point here. So let's consider the electric field due to this point. It's heading in this direction at this point A here. So let's call this angle in here theta. Then we can see that because this is a right angle triangle, this angle here will be 90 minus theta. So this angle here is going to be 90 minus theta as well. So if we were to split this electric field into a vertical and a horizontal component, then the angle theta is this one here. Now in the first part of the question, it asks us just to find the magnitude of the electric field. So we don't need to worry about the vertical and horizontal components. So we know that for a point charge, the electric field is given by kq on r squared. So in this case, we're finding just an increment of the electric field, and that'll be given by k. And then we'll need to know, well, how much charge is on this increment, and the charge is related to the length and the linear charge density through dq is equal to lambda dx. So we've got times lambda dx, and then we need to divide by the distance squared. So you can see from Pythagoras' theorem that this length of this side here is a squared plus x squared, and take the square root of that. So when we square that, we get rid of the square root. So it's divided by a squared plus x squared. So that's the magnitude of the electric field at this point due to just this one little increment. So that's part A. Now in part B, it points out that if we consider another point on this side here, then if we consider the electric field due to this one at this point A, it's going up like this. So if we split that into vertical and horizontal components, these horizontal components cancel while the vertical components add. So it's asked us just to find the vertical components because those are all we're going to need. So we'll have DEY is equal to the total electric field, this one, and then to get just the vertical component, if that's theta there, it will be times sine theta because it's opposite our angle theta. So now what we need to do is come up with an expression for sine theta because theta is not one of the variables given in the question. So let's look at this triangle here. Let's draw it again just to be really clear. We've got x, we've got a, we've got the square root of a squared plus x squared, and this angle in here is theta. So sine theta is equal to opposite, which is a, divided by the square root of a squared plus x squared. And so we can substitute that in here. So let's substitute in for dE. We've got k lambda dx over a squared plus x squared. For sine theta, we've got a over the square root of a squared plus x squared. So we can write this as k lambda a dx divided by, when we multiply these together, we'll end up with a squared plus x squared to the power of 3 on 2. Now in part C, it asks us to sum all of these increments together all along the wire to find out the total field at point A here. So I think the easiest way to do that is to sum from x equals 0 to infinity and then double it, because to account for the contributions from each side of the wire. The other way to do it is to go from minus infinity to infinity. So E is going to be equal to 2 times the integral from 0 to infinity of k lambda a dx over a squared plus x squared to the 3 on 2. And so we can write this as 2k lambda times the integral of a dx over a squared plus x squared to the 3 on 2 from 0 to infinity. Now this is just a standard integral which is on the formula sheet for this course. So looking at that, we can see we can write it as x over a root x squared plus a squared, and we're going from 0 to infinity. So this is equal to 2k lambda. Now if we're substituting in infinity, we'll need to take the limit. So on the top we've got x, on the bottom x squared plus a squared. The a squared is negligible compared to the x squared as x goes to infinity. So this is times a times the square root of x squared. And then we've got minus, we substitute 0 in here and we've got 0. So you can see x, and then we're dividing by the square root of x squared. So those will cancel each other out, and we end up with 2k lambda over a. So that's our expression for the electric field, and we can see from the diagram here that this is going vertically upwards.